Let's take a look at example 2 from section 11. In the previous example, we did some factoring algebraically. Now we'd like to use our algebraic factoring skills in a trig setting to help solve a trig equation. In the previous example, we only had expressions that were algebraic. We now have an equation that is trigonometric here, but our same concepts are still going to apply. My issue with solving this equation is it's difficult for me to know how much of this term I need to add to this term to be equal to 0. On the other hand, if we were doing multiplication of terms and arriving at 0, it's very easy for me to say that if I were to multiply any two numbers together and get 0, then either the first number is 0 or the second number is 0. That can help me solve the equation. So factored form is especially nice if we can be equal to 0 here. Since we're already equal to 0, factored form seems very desirable to me. So I'm going to ask myself, what can I factor out of each of my terms here? Well, what I see here as far as constants go is a 2 and a root 3. It doesn't seem like there's any nice common factor here as far as the constants go. If this was like 2 and 4, then I would probably factor a 2 out from everything. But I don't have anything that shares some nice common factors, so I don't think I'm going to factor out anything associated with my constants. The other terms that we have here are the sine of x terms. It looks like here we have 2 copies of sine of x. Here we have 1 copy of sine of x. So I could verbalize this as saying every term has at least 1 copy of sine of x. So that's what I'll factor out. If I divide out sine of x from each of my terms, the 2 has been left alone. We used to have 2 copies of sine of x, but we factored out 1, so 1 remains. We left the root 3 alone. We had 1 copy of sine of x, but we divided that out. Now I have my expression converted from an expression based on addition to an expression based on multiplication. The reason that this is very helpful for me is because I can say to myself, if a times b is equal to 0, then it must be the case that a equals 0 or that b equals 0. If you ever multiply two numbers and get 0, one of them was 0, for sure. So I can do that in this case here. Given my slightly more complicated expression, I can say, if I multiply this factor by this factor and get 0, it must be the case that either sine of x is equal to 0, or it must be the case that 2 sine x plus root 3 is equal to 0. These are both equations that I can solve in the interval 0 to 2 pi. First, let's solve our sine of x equal to 0, a little bit simpler here. I always like to stop and picture my unit circle here, and the question that I'm asking myself is, in the unit circle, when do we have a height of 0? What angle causes a height of 0? Well, I know where my height of 0 is on my unit circle. It's right there. And I can identify the 2 angles that are associated with this within the interval 0 to 2 pi. It looks like we're either interested in 0 radians or pi radians. 0 radians or pi radians are the 2 angles that result in a height of 0. So I think that these are 2 answers to this problem right here. Now let's come over and check out what's going on with our other equation over here. 2 sine of x plus root 3 equals 0. Well, I need to do a little bit of solving. This isn't in a very nice format for me yet. If I'm trying to solve for x, I'm going to at least work to get the x terms more alone. In this case, I'm at least going to work to get the sine of x terms alone. So I'm going to do some algebra here. 2 sine of x equals negative root 3. I've subtracted root 3 to the other side. Now I'm going to go ahead and divide by 2. So now I'm asking myself the question, on our unit circle, what angle gives a height of negative root 3 over 2? Starting from the middle here, I know that I've got to get to a height of negative root 3 over 2. And so I'm picturing these 2 angles down here as being the 2 that give me that height of negative root 3 over 2. If I am counting this in terms of radians, I'm seeing these as something like my pi thirds is out there, but I always forget which one. So I'm thinking to myself, 0 pi thirds, 1 pi third, 2 pi thirds, 3 pi thirds is just pi. It looks like this is going to be 4 pi thirds, and then 5 pi thirds. And this makes sense to me because one more gets me to 6 pi thirds, which is 2 pi, which is the same thing as 1 full revolution. So it looks like the two parts of my answer that I'll be getting from this equation are 4 pi thirds and 5 pi thirds. I hope by now we've all realized the intense value of knowing our unit circle here. And interpreting our angles from it here. For most of these problems, the key solving step for me when I go from my trig equation to my solutions is always picture-based. I draw one of these pictures every single time I'm ever solving any sort of trig equation whatsoever here. So keep drawing your unit circle, keep being comfortable making those pictures here to help get at all of our solutions. So to wrap this up, we would say that within one full revolution from 0 to 2 pi, it seems that there are 4 total answers to this equation. There are 4 different angles that result in this original equation being true. Finally, to kind of verify this one last little step, what I would suggest that you do is go to Desmos, throw in just this expression into Desmos right here. Don't put the equals 0 on the end right there. And what you'll see is that this equation or expression as you've entered it into Desmos will hit the x-axis because the y value is equal to 0, so x-intercepts at these 4 locations in the interval from 0 to 2 pi. So you can verify this guy in Desmos as well.